Hi, welcome back to this course on computational thermodynamics and kinetics of materials. Today we will do two important things. We will see some exercises on how to use Gibbs energy composition plots for some complex systems. We'll basically go back from phase diagram to the GX plots. Then we will cover Gibbs phase rule. Now, we will go back from the phase diagram to the Gibbs energy composition plots. In that way, we will have a much better understanding or appreciation towards this Gibbs energy composition plots. Now, we have this sort of binary phase diagram, AB system, and we will first understand this binary phase diagram and then see at different temperatures how do we get Gibbs energy composition plots. Right, so in this system what we have is high temperature single phase liquid, and then there is a single phase solid alpha throughout the composition range. So meaning A and B elements are nicely mixed in this single phase, but below this temperature we have these two phases coming, alpha 1 and alpha 2, same crystal structure and different chemical compositions. This is sort of immiscibility between A and B. Okay, this is how the system is, and here we have a two phase region, alpha plus L. This is also the same region. This is a continuous region, two phase region, and here we have a two phase region. So this is a binary system with low temperature miscibility gap. Okay, this is a miscibility gap. So high temperature there is nicely miscible. So in solid state we have at high temperature single phase alpha, that is A and B are miscible, and below a critical temperature, which is this point here, alpha 1 and alpha 2, two phases are in equilibrium, and A and B become increasingly immiscible as the temperature decreases below the critical temperature. You can see that the tie line actually will expand like this. It means that A and B become increasingly immiscible. Right. So when we want to plot the Gibbs energy composition plots for this, how many curves should we consider? How many phases should we consider to be in competition? So we are going to use liquid and alpha. Why? Because for one crystal structure or one structure, we said one curve will come. For liquid, there will be one curve. For alpha, there will be one curve. For alpha 1 and alpha 2, since alpha 1 and alpha 2 belong to the same crystal structure of alpha, we will have only one curve in which we will have to identify the compositions corresponding to alpha and alpha 2 by common tangent construction. But there will not be any separate curves for alpha 1 and alpha 2. So these three phases will have only one Gibbs energy composition plot. Right. Now let's consider one of the temperatures, high temperature T1, where it's a simple phase equilibrium from left to right. If you see, there is only liquid being stable in this temperature. So if we plot these two curves at T1, temperature T1, Gibbs energy versus composition, one for alpha, one for liquid, the alpha curve will be above the liquid curve throughout the entire composition range. It directly tells that liquid phase has the lowest Gibbs energy and it will be stable. So this is straightforward. Now this temperature here is more complex. If you see from left to right, you have this single phase alpha region, then it goes into two phase region, again single phase liquid region, then it goes to two phase region, and then single phase again alpha region. Okay, this is quite complex. If you see tie line information, this two phase region is here, so we can draw a tie line there. The tie line will start from this A point and end at this B point. Similarly, this side, the tie line starts at this C point and ends at this D point. Okay. We need to get this tie line information from common tangent construction. You remember common tangent where it touches two phases, two phase Gibbs energies. Those points, those composition points basically gives the tie line in the phase diagram, right? So we need to find this tie line and then this tie line. So two tie lines should come, therefore two common tangents should come. Let's see how does that come. So this is how the curves are. Now you have to carefully construct this if you have to come back from the phase diagram to the curve. So liquid is going deeper, coming like this, and the solid alpha is like this. Only when you have this kind of liquid plus solid curves, you will have a tie line going like this is a temperature T2, a tie line going like this where it touches A and B points. So if you take these 2 points, correspondingly you can mark it in the phase diagram against temperature T2. Similarly, in the right side you will have C and D. These two are also touched by one single line, right? So this is a common tangent to liquid and alpha curve. It is touching at C and D. Therefore, this will translate directly to the phase diagram as tie line information. You see, we have two common tangents coming and both are actually touching the same two curves, but they give this sort of construction where we get two tie line information. And in between this B and C, this curve is the most stable one, right? If you draw tangent to any points between C and D, you will see that no Gibbs energy curves will lie below that. Therefore, in this region between B and C, it is only this liquid that is stable. So that also you can see in the phase diagram, between B and C, only liquid being stable, right? And before this A, at any point if you draw a tangent, it will be below all the G curves. Therefore, the alpha phase will be stable below the A point, and beyond this D point, it will be only this alpha curve. Therefore, you see before A, it is all alpha, and beyond D, it is all alpha. Okay, this is how Gibbs energy versus composition plot translates to phase diagram. We have actually come from the phase diagram to the GX curve like this. So you have to imagine if somebody puts a line like this and asks you how G versus X will look for this, you should be able to come to this. Why this exercise is important is because different phase equilibria in a phase diagram is basically the competition between the phases in the G versus X like this. So if you are able to imagine this front and back, then you are becoming well versed with what is happening from the thermodynamics of phase diagrams. And that is the exact thing that is used in the software tools that we are going to see in future classes. So this is quite important. Now temperature T3, EF, these points should come, and since we know these 2 points should have the same crystal structure, we have to have one crystal structure, one Gibbs energy curve in which 2 points should be touched by a tangent giving this tie line EF, right? So this is how you get this E and F points basically from a curve which has some miscibility gap. So this change in curvature is an indicator that there is a miscibility gap, and two elements would try to separate out rather than being a single phase, right? Now one more system, slightly more complex. What if that small miscibility gap that we saw in the previous slide becomes larger and larger? Eventually it will come to this sort of phase diagram, an eutectic system. Okay, here alpha 1 and alpha 2 are there on both sides. There is no single phase alpha region anywhere. Okay, this is how the eutectic system looks. So in solid state we have similar crystal structures, alpha 1 and alpha 2. These are both similar crystal structures. So you can imagine the Gibbs energy composition curve should be only one curve where a common tangent touches 2 points. So let us first take that into consideration, the common tangent touching 2 points. So this is a solid curve here, and liquid curve is like this. We need to know this point and this point. So in this diagram, G versus X, just to help you, this alpha 1 plus alpha 2 and alpha 2 regions are marked. Okay, actually this is not a phase diagram. This doesn't have a meaning to say that at this composition and at this Gibbs energy values there is some stable phase. It's not like that. This is basically to indicate that between these 2 points, 2 phases are in equilibrium for these overall compositions, and before this and beyond this phase alpha 1 and alpha 2 respectively are in equilibrium. So this information is translated to phase diagram like this. So this is what T5 temperature diagram looks like, right? And at T4, one of the new things that you are going to see is T4, because at T4 you see alpha 2 and this horizontal line alpha 1 is there. In this horizontal line liquid is also touching here, meaning at eutectic temperature we have 3 phases in equilibrium: alpha 1 with this composition, liquid with this composition, and alpha 2 with this composition. Okay, so we need to have 3 curves or a common tangent touching in 3 points in the G versus X diagram. So this you can see, this is the solid curve and this is the liquid curve, and in one tangent, one common tangent, all three phases touch. And you have this three-phase equilibria coming in because of that. Now if you go to really high temperature T1, we have liquid being stable throughout, therefore solid will be above that. And at temperature T2 has this two-phase equilibria here only in this A-rich compositions. So that has to be reflected here. You see the solid and liquid have this sort of intersection, and common tangent is drawn like this, so that this point and this point, which can translate to this liquid plus alpha tie line region here, right? Then at temperature T3 here, something similar to what we saw in the previous slide, where we have two tie line information coming, one from here to here and one more from here to here. Therefore liquid should be plunging into the solid state Gibbs energy, so that you get this two common tangents. You can translate this composition information here and read the tie line. So if you feel it's slightly difficult to understand, pause, see carefully how these things translate to one another. With that you can test your understanding for this system, where we have two alpha plus beta different crystal structures on two sides. So two different G versus X curves are required, for one for alpha and one for beta in solid state, and then one liquid curve is required. So three curves should be used to understand the G versus X for these different temperatures T1, T2, T3 and T4. Now you can pause, try it out yourself in a notebook. Once you are ready with the answers, you can play and see the answers. So let me show the answers now. At temperature T1, here you have this two tie line information, tie line coming here between liquid and alpha. So you need to have this alpha curve and liquid curve touching a common tangent corresponding to these two compositions. These two compositions are important, so you can mark them here and here, right? At temperature T2, we have something similar to what we saw in last two slides. There is a two-phase equilibria, and then a single phase, and then again a two-phase equilibria. But this is between liquid and alpha here, this is between liquid and beta here. So in that way, liquid should be plunging to solids, so that you have one solid liquid equilibrium here, another liquid solid equilibrium here. Then at temperature T3, it's a eutectic temperature, therefore a common tangent should touch three phases, alpha, liquid and beta, corresponding to the eutectic compositions. At temperature T4, we have two phases, alpha, beta. The liquid should not be stable, so bring liquid up, take alpha and beta in the bottom, make them touch a common tangent corresponding to these two compositions, this one and this one, these two compositions, right? So I hope you are able to get the hang of it. One more, let us slightly push our understanding and put it for a slightly more complex case, peritectic and eutectic. In this case, we have in solid state alpha, beta, gamma, three phases, and then a liquid phase. So four curves should be there. Let's see how it comes. At temperature T1, four curves are there, but liquid is the most dominant one throughout. Okay, alpha, beta, gamma are not drawn throughout the entire composition range. Because of their existence range here, alpha is stable only in this left extreme, beta is stable somewhere in the middle, gamma is stable in the right extreme. Therefore, it is chosen like that. At temperature T2, we have this peritectic reaction coming, where alpha plus liquid gives a new solid beta. So we need to have alpha, beta and liquid touching each other. Alpha curve, then beta curve, then liquid curve. Liquid will be in the right extreme or left extreme in peritectic reaction. In eutectic, it will be in the middle. Okay, so this is how the compositions of three phases are. Now at temperature T3, we have a two-phase equilibrium, single phase, again a two-phase equilibrium. So whichever phase comes as stable in the middle, Gibbs energy of that curve should be slightly more plunged down. Therefore, you can draw a common tangent, one on left side, one on right side, and mark the compositions for two-phase equilibria. And then comes slightly more complex one, where at temperature T4 we have a single phase, two phase, a single phase, again two phase, a single phase, again two phase, again a single phase. Okay, quite complex. So at least 3 tie lines should come. Here one, and here one. So 3 common tangents should be there. Seen here, you can see beta is slightly plunged so that you can draw a tangent in the left side and right side of beta. And here between liquid and gamma, there is a common tangent. Okay. So this is between liquid and gamma, there is a common tangent. That is also drawn carefully. So the curve's positions are to be selected in such a way that you are able to get the phase diagram. This is a temperature T5 where we have a two-phase here, two-phase equilibria and an eutectic reaction. So a line touching 3 phases and a line touching 2 phases. Both are coming here. Right. So that's about binary G versus X. We'll see a small flavor of how it looks in the ternary regime. These are not Gibbs energy curves, these are Gibbs energy surfaces. Okay, 3 element composition space. So we have Gibbs energy surfaces coming, and you can see alpha, beta, gamma, liquid. 4 surfaces are there hanging, and this is one corner of that where you see there is a solid liquid, this is a solid surface and this is a liquid surface. Okay, they intersect like this, and this information, there is a tangent touching, but it is not a tangent line, it is a tangent plane. Okay, you see, if surfaces are hanging, you need to have a plate to touch that, right? So in that way it becomes a common tangent plane. And this is the case with the ternaries. So this is for a ternary space, right? In ternary space, we have these surfaces, 3-dimensional things, where a common tangent plane touches the things, right? In quaternary or higher order, you can't even imagine pictures like this. Of course, the common tangent plane is going to become a common tangent 3-dimensional object, right? In quaternary itself, and its dimension is going to increase as we go to higher and higher order. But the advantage with this CalFAT tools is this: you have Gibbs energy versus composition against temperature in the form of equations, right? So you have Gibbs energy functions. So mathematically, any dimension can be handled. So that's the advantage we have with these tools. So this translates this surface, wherever it touches these surfaces of liquid and solid Gibbs energies. You can see it is like a line here, and there are multiple lines touching solid to liquid. They all translate here as tie lines. Okay, this is how you get the ternary tie lines. This is a ternary phase diagram coming from G versus X of ternary. Right. So now we are done with that. We are going to see one more important idea called Gibbs phase rule. Why Gibbs phase rule? What is it? What does it do? Is basically it helps us describe the phase equilibria with independent variables. Okay, here in this diagram we have a two-phase equilibria, right? Alpha 1 plus alpha 2 at this temperature, and G versus X plot gives you these two points where those compositions are seen. Now, how to describe a two-phase equilibria? That is alpha 1 plus alpha 2 here. Okay, this is an example now. Given that number of components are 2, A and B, and number of phases are 2, alpha 1 and alpha 2. Okay, how do we define this, and how many independent variables are required to define this? Now there is something in gray color here, which is actually not the right answer, but this is where we start. Our number of independent variables 4. Why we are asking this? Because we know pressure is one independent variable. Of course, we are keeping pressure as constant in these phase diagrams and all, but it is still a variable which can affect the phase equilibria. So we have to say pressure is one variable, and temperature of course is another variable. These are independent. Then third and fourth variable are X of B, mole fraction of B in alpha 1 phase and in alpha 2 phase, the points E and F here. Okay. So this is how we feel like defining. XA we don't need to XA we don't need to tell because XA depends on XB. XA in alpha 1 and XA in alpha 2 is dependent because it is just 1 minus XB. So this is what we think. Two composition variables, one pressure and one temperature are required to define this two phase equilibria alpha 1 plus alpha 2 in this two component system AB, right? But the right answer is number of independent variables are only 3. One is pressure, other one is temperature, and third one is XB in only one phase alpha 1. Okay, we are talking about this composition here. Only this composition is independent and this composition here is dependent on it. XB in alpha 2 depends on XB in alpha 1. It is a dependent variable. Okay, due to mu B being same in alpha 1 and alpha 2. See here mu B, we are marking one chemical potential of B for alpha 1 and alpha 2. That is the meaning of common tangent, right? So if this is so, then one variable XB in alpha 1 is the only independent variable and XB in alpha 2 becomes dependent on that. How? We will see that in the next 3-4 slides. That's where Gibbs phase rule comes. So this is what we are going to see in Gibbs phase rule. How many independent state variables are required to describe a phase equilibria? Temperature, pressure and composition variables, but how many number of composition variables? That needs further clarity. Let's focus on these composition variables. I'm going to explain this in two ways. One, with an example of a 3-element system and two-phase equilibria. Other one, generalizing the same. Okay, if I go directly to the generalized version, it sounds a little difficult to understand for many people. So I'm putting an example first and then go there. So consider one phase alpha with number of components 3, A, B and C, a 3-component system, and in that we know mole fractions of 3 different elements A, B, C in alpha put together should be 1. Compositions of 2 components are independent, we know that, because composition of the one component, let's say the first component, is nothing but 1 minus the other things. Therefore this thing becomes dependent on the others. Okay, so only 2 are independent in a 3-component system. 2 composition variables are independent. So in a two-phase equilibrium, now this is about one phase, right? In alpha phase this is true. If we have 2 phases alpha and phi, then 2 multiplied by 3 minus 1, the same 3 minus 1 we are taking here and multiplying that with 2 because there are 2 phases. That many composition variables are independent. This is what we would like to conclude. But are they? We will clarify that by considering this chemical potential of beta, so chemical potential of B in phi, which is mu B in standard state plus RT natural log of activity of B, right? So this activity of B is going to be a function of XB, isn't it? If it is an ideal solution, AB is equal to XB. If not, AB will be deviated from XB. But in any case, it is a function of XB, right? So we can write mu B in phi is a function of XB. Then if we say alpha and phi are in equilibrium, then we need to say that chemical potential of B in alpha is equal to chemical potential of B in phi. So this is function of XB in XB alpha, this is function of XB phi. So in case XB alpha changes, then mu B alpha will change accordingly. If mu B alpha changes, then mu B phi should change according to this change because these two are equal. If this is changing according to this, then XB in phi will change according to this, right? So if XB in phi is changing according to XB alpha, that means this is dependent on XB alpha. It is not independent. Okay, so only XB alpha is independent, XB phi is dependent on it. That is, one independent variable is enough here to define composition of one element, let's say B, in 2 phases. If you define XB in only one phase, that is good enough. Okay, so now we have 2 phases. So 2 minus 1, which is equal to 1, that many number of dependent variable of B's composition are there. Okay, if there are multiple phases, you can imagine what will happen. So in this case, 3 components are there. Now this is only for B's composition, right? We are talking about only B here, and we started with A, B, C 3 elements. So 3 components, if we take 3 multiplied by 2 minus 1 variables are dependent. So this many variables are actually dependent. We thought so many are independent, but among them these many are dependent now. Therefore, we take this total, these many independent we thought, we will take that, and from that we will subtract these many dependents that we figured out from this chemical potential equality. Okay, so only these many composition variables are independent. So I am putting a generalized form of the same. Consider one phase alpha with components C, not putting 3 here, C number of components. Therefore, XA, XB, XC plus any number of elements, whatever is this C, that many mole fractions if you add, it is going to be 1. Therefore, C minus 1 components compositions are independent. For only one component, you can say 1 minus summation of all other components will come. Therefore, one variable among all these is dependent. So in a P phase equilibria, P is the number of phases now, then P multiplied by C minus 1 composition variables are independent, but based on chemical potential we are going to prove that is not so. Mu B in phi is mu B standard state plus RT ln of AB, which is a function of XB. Therefore, in multiple phase equilibria alpha, phi, etc., the chemical potential of this element B is going to be same. Therefore, the XB alpha becomes the only independent composition variable for B. All others will be dependent on that. If the value of XB in one phase, let's say in alpha, is fixed, then XB in other phases have to be dependent on it. They also must be fixed. Right? So in a P phase equilibria, P minus 1 variables of one component are dependent. Only one compositions variable is independent. Only one composition variable is independent for one component. So if we have multiple components, let's say C number of components, we have to multiply this P minus 1 with C. Those many will become dependent. So we have to subtract this thing from the totality of variables that we considered initially. So in a C component system, we thought P into C minus 1 composition variables are independent due to sum of mole fractions equal to 1. So only one, the C minus 1, only one is dependent, all others are independent we thought. But more importantly, we figured out C into P minus 1 are dependent due to the criteria of equality of chemical potentials. Therefore, independent composition variables will be the difference between this total and this guy, P into C minus 1 minus C into P minus 1, okay, which turns out to be C minus P. Okay, so apart from this, we have two more variables, P and T. These are also independent, so we need to add them. The total number of independent variables, this is the important thing we are going to conclude. The total number of independent variables, other name is variance, or most commonly used word is degrees of freedom. How many degrees of freedom are there? Meaning how many independent variables are there to define a phase equilibria? F is equal to number of components minus whatever is the number of phases in equilibrium plus 2. This 2 is coming because of P and T, otherwise it is only C minus P. So this is the total number of independent variables required to define a phase equilibria. The most of the cases that we consider are where the pressure is kept constant, right? So we don't need to give this plus 2, we can just use plus 1 here because we know pressure is going to be constant. Okay. So F is equal to C minus P plus 1 will give us, in most of these phase diagrams that we see, what is the kind of independent variables required to define the phase equilibrium. So what is the meaning of it? Let's see how Gibbs phase rule applies to a binary system. Let's think about this point here, point 1. Okay, this point 1, according to Gibbs phase rule, F is equal to C minus P plus 1, right? How many phases are there here? Alpha phase, only one phase. How many components? A, B, 2 components are there. Okay, then F is equal to 2 minus 1 plus 1. Number of components 2, phases 1. So F turns out to be 2. What does it mean? It means that either XB or temperature or both can be varied and single phase remains in equilibrium. Okay, for example, if I change the temperature from here to here. The single phase equilibrium is still there. Alpha is still in equilibrium, right? So when T changes, XB need not change or move to a specific value. When we see the next slide where we apply it to two phase region, you will realize this, how XB need to move there. Okay, here XB need not move to any other value. It is independent of T. Okay, XB can remain the same or it can change to some other number also. It need not change to a specific value, XB. Okay. And similarly, when XB changes, T need not change or move to a specific value. It is independent of XB. Meaning, if from here, if I go to left or right, I am changing composition, right? And I will still have alpha in equilibrium. So, if I perturbate it little bit, will I remain in the same phase equilibria? That is the question. That perturbation is what movement of variables we are talking about. Okay. So, here if we perturbate in the composition or in temperature, we are not going to see any change in this alpha single phase equilibrium. So, that is why we say degrees of freedom are 2 in this case. Now, if we consider this point here number 2, I am putting this line intentionally in blue color. So, if we consider this point 2, this is also two component system AB, and how many phases are in equilibrium here? Alpha plus liquid, two phases are in equilibrium. And if we put a tie line, we can read the compositions XB alpha, XB liquid, and we know XB alpha is the only independent one and XB liquid is going to be dependent on that. So, we are going to talk only about XB alpha as a variable along with the temperature. Okay. What happens here is, for this entire range of overall compositions, these two phases alpha and liquid with these two compositions, alpha will have this much amount of B in it remaining A, beta will have, liquid will have this much amount of B in it remaining A. So, if I change the temperature now at this point to a higher temperature like this here, then what happens? I change the temperature. Can composition remain the same? XB alpha, can it remain here? No, because tie line is here. Tie line tells you if two phases are to stay in equilibrium, the phases should have this composition and this composition, right? So, XB alpha should change to this new value. XB alpha should shift to the left side. Okay. So, the content of B in alpha phase changes if temperature changes. That's the difference here compared to the previous case. So, in a two phase equilibria, if we calculate based on Gibbs phase rule, number of components 2, number of phases 2. Okay. How many degrees of freedom we get? 1. What does it mean? Any one of these two, XB alpha and T, can be changed, can be varied, and two phases remain in equilibrium. Okay. When T changes, XB alpha must change to a new value along the blue line, right? Along this line, it has to change from this composition to this composition. Okay. Along the blue line, two phases to remain in equilibrium. Otherwise, two phase equilibrium will be disrupted. Okay. Therefore, we call it monovariant. Okay. This equilibrium is a monovariant equilibrium. This two phase equilibrium in this entire range is a monovariant equilibrium, meaning only one variable can change independently. So, in a three phase equilibrium, now this eutectic line we are choosing from left to right, we will have three phases in equilibrium for all these overall compositions. More importantly, we have these three composition. Alpha composition should be this, liquid composition should be this, and beta composition should be this. Okay. So, if we apply the Gibbs phase rule for three phases in two component system, we will get degrees of freedom 0. What does it mean? None of these variables, none of XB alpha and temperature can be varied to have three phases remain in equilibrium. So, if you change the temperature, of course, three phases are not going to be there. We see that here. If we change the composition of XB alpha from this value to any other value, okay, if this line or this line, any other value, if you try to change it from here to left or right, you are basically disrupting the equilibrium because three phases cannot stay in equilibrium. You remember the Gibbs energy composition plots, three Gibbs energy curves touching a common tangent. That's what is reflected like this, right? So, if you change the composition of beta, the point where the tangent touches. Okay, any other composition of beta, alpha cannot stay in equilibrium with the other two phases. So therefore, the composition of alpha, xb alpha, should be this particular value here. Otherwise, three phases cannot stay in equilibrium. Okay, so example, when temperature changes, three-phase equilibrium does not exist no matter how xb alpha changes. Similarly, if xb alpha changes, no matter how T changes, equilibrium does not exist. This three-phase equilibrium will be distant. So that's the meaning of three-phase equilibria having 0 degrees of freedom. Because of this, it is called as invariant equilibria. Okay, so this is a invariant equilibria, three phases staying in equilibrium in a two-component system. If we increase the number of component to 3, then degree of freedom will be 1. Meaning in a 3-component system, to have 3 phases in equilibrium, it is a monovariant phase equilibrium. Right? So in these binary systems, because of this nature of all these horizontal lines which have 3 phases in equilibrium, all these reactions, they are called as invariant reactions. And that is also quite commonly used name for eutectic, eutectide, peritectic, all these reactions. The name is invariant in binary space. Right. So degrees of freedom in a phase equilibrium are given by Gibbs phase rule. We are using the word degrees of freedom here. We have to be little careful. Here degrees of freedom are composition of an element in a phase, for example xb alpha in a AB binary phase alpha, along with pressure and temperature. This is what we say as degrees of freedom. But previously we have come across this word. Okay, this is not to be confused with the degrees of freedom of atomic motions to cause heat capacity. Remember, for heat capacity we said there are vibrations, there are 3 vibrational degrees of freedom, x, y and z directions. That is also degrees of freedom. So don't confuse that word here. Secondly, more importantly, from the next class onwards, we will do computer calculations, hands-on calculations. When we do that, we will use this word degrees of freedom again, but there it will mean different variables. It is not the things that we are talking about in the Gibbs phase rule. So we will see that in the next class. Thank you. I hope the lecture is useful. See you in the next class.